Yes, sir, I hope I am audible.
Yes, sir.
Okay. Surakandan sir, am I audible?
Yes,
sir, you are audible, sir.
Yes, sir. Yeah, thank you, sir. Thank you so much.
Shall we start, sir?
Yes, sir.
Yes, sir. Please.
Live, sir.
Okay, sir.
Now I invite Dr. Saraswathi Swami sir to invite Organization, sir.
Warm good morning to one and all who gave their presence, valuable presence for this one-day seminar organized by the Department of Mechanical Engineering, Nadar Saraswathi College of Engineering and Technology. Now I would like to welcome Mr. V. Sivaganathan to propose the welcome address. Sir, you are welcome, sir.
Yes, sir. Good morning to everyone present here. It is my pleasure to welcome you all. First of all, I would like to thank our management to give the wonderful opportunity for this seminar. I heartily welcome our college secretary, Mr. K.S. Kasuprabhu sir, and joint secretary, Mr. A. Rajkumar sir. I would like to welcome our eminent leader, Principal Dr. C. Madalai Sundaram sir, Vice Principal N. Madhavan sir, and Academic Coordinator, Placement Officer, Dr. C. Karthikeyan sir, for this good occasion. I extend my welcome to today's speaker, Dr. V. Dhinakaran, Professor Mechanical, Chennai Institute of Technology, Chennai. And I extend my welcome, HOD of our Mechanical Department, Mr. A. Vembat Rajesh sir, and the Coordinator, Dr. C. Sivaganathan sir. And our faculty members, participants, internal and external, welcome you all once again. I am giving the portion to Dr. Sivaganathan sir, giving the address of our chief guest. Thank you.
Thank you, sir, Sivaganathan sir.
Yes.
You are valuable. It is my immense pleasure to introduce today's chief guest, Dr. V. Dhinakaran. Dr. V. Dhinakaran is an experienced professor with a demonstrated history of working in the higher education. Head at Center for Additive Manufacturing in the Chennai Institute of Technology, Chennai. Currently, he is working as Dean Research and Development. The expertise is skills in engineering, finite element analysis, and computational fluid dynamics, composites, welding, additive manufacturing, and various other fields. Dr. V. Dhinakaran is the author of abundant articles in peer-reviewed journals, as well as he is the author and editor of various handbooks in research areas published with Elsewhere, Taylor and Francis, and Springer. He is an associate editor in Journal of Robotics and Control and editorial board member in American Research Journal of Biomedical Engineering. Editorial board member in Youth, editorial board member of Advanced Powder Materials. With this background, sir, giving today a seminar on additive manufacturing. Thank you. Thank you for this opportunity. Now I welcome Dr. V. Dhinakaran to take over the session. Thank you, sir.
Yeah. Thank you, Surakandan sir. So good morning to one and all. It is my great pleasure to be a part of this one-day national seminar conducted by Nadar Saraswathi Engineering College. So we thank all the authorities of Nadar Saraswathi Engineering College for giving this opportunity, and I congratulate the organizing committee for successfully conducting these events. And also I thank our management of Chennai Institute of Technology for giving me permission to disseminate my knowledge in this wonderful forum. Let me share my screen. I hope my screen is visible, right, sir?
Yes, sir.
Yeah, sir. Super.
Yes, sir. This. So today topic of lecture will be on additive manufacturing. So I am going to give you the overview of additive manufacturing. I am not going to present much more results. I'm going to introduce additive manufacturing to this wonderful forum. And certainly, I should that this fundamental of additive manufacturing will help you to learn further and enter into your research area. So additive manufacturing, the necessity for additive manufacturing is due to the reduced part cost, and the material wastage will be much more reduced, and the time to the market of the additive manufacturing part will be very less. These are the three major advantages which makes additive manufacturing to be familiar among all the researchers and all the communities nowadays. And it also increases the design freedom. So how it increases the design freedom? So when you want to manufacture a component using additive manufacturing, it reduces the number of subcomponents. For example, if a component or if an assembly is made up of more than 10 components, when you go for traditional manufacturing system, then the 10 components have to be assembled together, and that they have to be assembled together by using any temporary or permanent metal joining processes in order to form an assembly. But when you go for additive manufacturing, you do not need to manufacture the individual subcomponents. The number of subcomponents required to form an assembly may be drastically reduced, because of which there will be a lot of weight saving, which increases the design freedom. And also, as I said, the subcomponents will be very less. And these are the advantages which makes the additive manufacturing to be spelled out by all the communities. So I want to, this one, how to hide this? Any idea? Am I audible?
Yes, sir. Yes, sir. It's audible, sir.
So can this be hidden?
Sir.
This bar is visible to you. This control panel. Not visible to you. Right. Oh, good. Right. Okay. So additive manufacturing, if you look into any additive manufacturing system, there will be three important systems. One is motion system, heat source, and feedstock. So material has to be melted by any heat source. Then it has to be deposited on the surface, deposited on the substrate material, layer by layer. In order to achieve this, for any additive manufacturing systems, this motion system, heat source, and feedstock material, these are the three important systems which will be the constituent of any additive manufacturing machine or equipment. So let us see how the formative versus subtractive versus additive manufacturing are being. So when you go for formative manufacturing system, you need to make a die or mold. Then you have to pour the molten material in case of casting. Okay, you have to pour the molten material. Then it has to be carefully poured. Then the material has to be taken out. Then it will be subjected to post-processing in order to get a good component. Okay. So in the traditional formative manufacturing system, if you want to manufacture the particular component, then you need to spend a lot of time in designing the mold or die. Then it will increase the lead time to send the product to the particular market or to send it for assembly. And if you are not properly, or if you are not carefully doing this operation, you will be ending up with the different defects, which may not yield the correct property of the material, because of which the material cannot be useful. Hence, the careful operation is needed when you go for formative manufacturing system. When you go for subtractive manufacturing system, then you need to process the raw material with any material processing technology in order to obtain the finished products. Okay. So if you look into the final product, almost the volume of the final product is only 50%. So the subtractive manufacturing will reduce the volume of the raw material, by which the lot of materials will be wasted, which will increase the cost of the equipment or cost of the assembly which is being manufactured. Hence, the subtractive manufacturing consumes a lot of costs. Okay. And also, you need to carefully choose the material processing technology, because the material processing technology, what you choose, should not affect the properties of the material. Okay. So you see, when you process this material, the material is being removed with the help of due to the friction. So because of the friction, the heat will be generated. Due to the heat generation, the mechanical and metallurgical property of the material should not be affected. Okay, so carefully you need to choose the material processing technology in order to ensure the correct strength and metallurgical property of the materials, right? And also, as I said, lot of materials are getting wasted, because of which almost 50% of the materials are being wasted in order to obtain the finished product. Then when you go for additive manufacturing, the material is manufactured layer by layer, and because of which there will be no wastage, and the required part can be obtained easily. Okay, so you do not need to worry about the material processing, since the material is manufactured layer by layer. So these are the difference between the formative, subtractive, and additive manufacturing techniques. So what are the steps involved in 3D printing or additive manufacturing? So first you need to create the 3D model. Then the 3D model will be converted into STL file, stereolithographic files. Then it will be transferred to the machine. Then it will be generating the G codes. Then the component will be manufactured layer by layer. Then the component has to be removed from the substrate material. Then it has to be subject to post-processing in order to obtain the finished products. How the additive manufacturing is being classified. So as I said, 3 systems are highly essential for additive manufacturing. One is heat source, then another one is feedstock material, another one is motion system, right? So the material will be melted first. The melted material has to be manufactured, or has to be deposited layer by layer in the substrate material as per the requirement. Okay, so it has to be moved as per requirement. For that, a motion system is required. Okay, here the heat source plays a major role. There are 2 types of heat sources are being used in additive manufacturing. One is beam heat source, and another is arc heat source. So beam may be either laser beam or it may be electron beam, and arc you can use the welding heat source, like tungsten inert gas welding heat source, or metal inert gas welding heat source, or plasma welding heat source. And while using the beam, you can use either a wire or a powder to which have to be melted, to form the final product. Okay. On electron beam also, you can use either wire or powder. And the powder either can be spread on the substrate material, or it can be blown on the substrate material. It can be blown on the substrate material, and when it is spread on the substrate material for further processing, that is called selective laser melting. When it is blown on the then it is called as a direct laser fabrication. Okay, and the building heat source can use arc. Then the particular manufacturing process is called as wire plus arc additive manufacturing process. So based on the three systems, what I said, I have this classification is being defined. Okay, so motion system, you can, for the motion, you can use either robot, or you can use CNC machine, or you can use any manipulators or canneries for moving the particular heat source or the way to deposit the molten material. And the heat source, you can use electric arc or powder beam, as I said. And the material, you can use either wire or powder-based materials. So you can go for either a liquid feedstock material, or you can go solid feedstock material. You can, if it is liquid feedstock material, you can go for wet polymerization, or you can ink or binder can be used. If ink or binders are being used, then it is called as binder jetting process or material jetting processes. Okay, and the polymers, polymer material can be used. Polymer material can be used, and they can use the solid material. When the solid materials are being used, and then it is called as material jetting process. They can use the solid powder. Okay, so we will see all the process one by one in the forthcoming slides. Okay, you can use the powder or this powder phase fusion process, or direct energy deposition process, or material extrusion process. Okay, powder-based fusion process, direct energy deposition process, or material extrusion process. And the sheet, you can sheet also can be used for joining them together. Then that is called sheet lamination. Okay, sheet lamination. So I said binder jetting, powder bed diffusion, sheet lamination, and direct energy deposition. Okay, so under powder bed diffusion, you can use direct metal laser sintering, selective laser sintering, and selective laser melting, and electron beam melting. Okay, so there is a difference between sintering and melting. In the melting, the particular material will be brought to its melting temperature, whereas in sintering, the material will be heated to the 85% of the melting temperature. Okay, that means in sintering, the material will not be brought to its melting temperature. For example, if you look at the titanium melting point is 1950 Kelvin. If you use selective laser melting, that means titanium 6Al4, Ti64 alloys. When you go for a selective laser melting process or electron beam melting process, the titanium powder will be melted by bringing it to the temperature of 1950 Kelvin. Whereas when you go for laser sintering or direct metal laser sintering, 85% of the 1195 Kelvin will be achieved during this process. Okay, so with this temperature, the powder are fused together. Powder materials are fused together in order to form layer by layer in order to get the final product. Okay, so in the sheet lamination, so all the sheets are different. Different layers of sheets are arranged together. Then, due to the ultrasonic vibration, the sheets are binded together. That process called sheet lamination. In the direct energy deposition, there is an important difference between direct energy deposition and other process. We will see in the forthcoming slides. You can use electron beam, or you can use wire laser additive manufacturing, or you can use wire arc additive manufacturing. Okay, if you use the beam as heat source, to melt the wire, then it is called wire beam additive manufacturing process. If you use welding source as the heat source to melt the wire, then it is called as wire plus arc additive manufacturing process. So what are the materials which are being used for the additive manufacturing process? These are the common materials which are mostly used in the additive manufacturing industries. Or when you go for aerospace industry, aluminum, stainless steel, titanium, cobalt, nickel superalloys, and precious metals are being used in the additive manufacturing process. When you go for aerospace application, in the titanium and its alloy, Te6Al4V is one of the alloy which is highly used in the aerospace industry. So Te6Al4V is a alpha beta alloy. So it's a 12 base alloy, alpha beta alloy, which is often called as workhorse of titanium. Okay, so titanium and its alloy, there are a lot of alloys. Te6Al, titanium is called as there is something pure titanium, and it is called as grade 2 titanium. In the titanium family, there are different types of alloys, among which Te6Al4V is the highly used alloy. Okay, so because of its high usage, it is called as workhorse of titanium, and because of which it is highly used in the aerospace industry. And when you go for when you compare the aluminum, stainless steel, and titanium, the density of the titanium is lying between the aluminum and stainless steel. Okay, so aluminum may be 2,300 or 2,500 kilogram per meter cube, and stainless steel, you know that it is around 7,800 kilogram per meter cube. When you look into titanium and its family, it may be around 4,800 kilogram per meter. Okay, so the density is lying between the aluminum and stainless steel, but its strength is double the time of stainless steel and triple the time of aluminum. So because of which the titanium alloy is highly used in the aerospace industry. And also nickel superalloys. So for example, Inconel 625, Inconel 718, Hast alloy. Okay, so these are the superalloys which are being used in the additive manufacturing industry for aerospace applications. And the Te6Al4V is one of the alloy which has biocompatibility, because of which it is highly used in the biomedical industries to manufacture the knee hub or teeth or bones. Okay, so among the titanium and its family, Te6Al4V is having the higher biocompatibility and corrosion resistance. Okay, so because of which they are Te6Al4V is highly used in the medical industries. And because of the weight advantage, the strength to weight ratio, the titanium 6Al4V and titanium alloys are also used in the automotive industry, marine industries, and because of its measurability and weldability properties. Okay, and if you look into the table, stainless steel is being almost used in all the applications like aerospace, medical, energy, automobile, marine, and high temperature applications, tools and molds, making tools and molds, and consumer products. But when you compare the stainless steel and titanium, and the titanium is having lot of advantage except the cost of the material. Okay, so the cost of the material of titanium is very high when compared to the stainless steel, okay, and compared to other materials. So, and when you compare to the titanium, when you compare the titanium nickel superalloys, both of them are almost having same cost. So when you look into the applications of additive manufacturing in different fields, the automotive industry is holding additive manufacturing in its hand. So almost 31.17% of automotive industries are using the additive manufacturing process for its applications. So next, consumer products are being manufactured by additive manufacturing. Even foods are being manufactured by the additive manufacturing process. Then business machines are being manufactured. Then medical industries, academic, for academic research and for teaching purposes, the additive manufacturing process, additive manufacturing technology is being used in the academic industries, and aerospace industry, government sectors for making the military applications. This additive manufacturing process are highly being applied. And also, when you go for military applications, when you are in the emergency situations, when a common get failure, when a common is getting failure, you do not need to, you are unable to spend much more time to make the commons, because of which the additive manufacturing will not consume much more time to manufacture the component, because of which the additive manufacturing process is being used in the government or military purposes. And also, among this additive manufacturing process, wire arc additive manufacturing is one of the process which is being familiar for repairing applications. When a particular component is getting failure in the equipment, when some military operation is happening, so you without replace, you do not need to worry about replacing the entire component. You can use the wire arc additive manufacturing process to repair the component. Okay, so the wire arc additive manufacturing process will be able to deposit the particular or fill the material, repair material. Then that can be subject to the post processing, which will ensure the correct strength of the material as it is purchased. So it is being used for innovative sustainable design. Additive manufacturing helps to have innovative sustainable design. So because, as I said, a lot of materials are being wasted, and also it reduces the different subcomponents in forming the assemblies, and it will give you the touch and feel effect. You can readily print the material, and you will be able to analyze the survivability of the particular product, because of which it gives some innovative design freedom when you go for additive manufacturing, and also it increases the overall quantity of the quality of the design. So it will help us to meet the environmental targets. Okay, so the reusability of the additive manufacturing wastage will save the environment. And so 3D printers can melt, fuse, and bind or center the exact amount of the material needed for manufacturing a particular component, because of which the sustainability in the environment is being achieved. So it reduces the overproduction possibilities when you know the exact need of the components are being defined. Okay, so the manufacturer can create greener process and the manufacturing environments. Okay, so the additive manufacturing is helping us to have a sustainability environment in all the ways. Okay. So as I said, it reduces the material wastage. So as I said, when you do not need to produce the much more subcomponents for manufacturing the particular equipment or machine, then absolutely the machines will be operated for lesser amount of time, because of which there will be lesser energy consumption, and because there are much more demand for energy, and even we are taking a lot of steps to produce energy. There is always demand for energy. Okay, so when you go for additive manufacturing, when you consume the lesser energy consumption, certainly there's a very big advantage. So the recycling of material is always possible when you go for additive manufacturing. Then, for example, the FDM printer is available everywhere. So you will be able to reuse the waste product to make the filaments. So which also indirectly contributing the sustainability of the environment. So you'll be able to manufacture the eco-friendly products by, so for example, when you go for fusion deposition modeling, PLA is a material which has the which is biodegradable, sustainable, and non-toxic, and which contains minimal wastage. Okay, so when you use this type of materials, then certainly you will be able to manufacture eco-friendly products. And you can produce the innovative products when you go for additive manufacturing. So additive manufacturing will help to implement green manufacturing, and it helps us in the sustainable supply chain. So these are the advantages of additive manufacturing. Okay, so additive manufacturing is reducing the material wastage, reducing the time to market the products. Then it increases the design freedom. So these are the advantages which makes the additive manufacturing to apply almost in the all the fields. In mostly in the forthcoming years also, most of the consumer products also will be used in additive manufacturing, and the cost of additive manufacturing will be very less when you go for much more product manufacturing. And also, as of now, the additive manufacturing is not helping to manufacture product in mass way. However, the technology will help us to achieve this in sooner. So additive manufacturing, I said, the direct energy deposition is one of the important additive manufacturing process, where the metal or any material will be melted, then it will be deposited on the substrate material. So we will see the difference how the direct energy deposition is giving the advantage compared to the order built fusion process. But here you should understand the direct energy deposition process. Direct energy deposition process means directly by applying the energy, heat energy in the material will be melted. That means when it comes out from the particular nozzle, or when it reaches the substrate material, it will be as liquid. It will be as liquid, or it will be in a molten condition in order to be deposited on the substrate material. Okay, so that is the direct energy deposition method. So in the direct energy deposition, you can use either laser beam heat source or electron beam heat source, or you can use what we call building heat sources. Okay, so we can let me play a video so you can better understand. See, the material is coming. The material is coming, and the material is melted by using the laser heat source. And the molten material is deposited on the substrate material. Okay, molten material is deposited on the substrate material. So the material is directly heated by the laser heat source, and the molten form of the material is obtained. And it is deposited on the substrate material. Okay, so since the material is directly heated to the molten stage, so this process direct energy deposition process. Directly, the molten material is molten stage is obtained somewhere, and it is deposited on the surface. Okay. So you see this operation, you are able to see the deposition rate to be higher. Deposition rate here compared to the previous one. Okay, so here the deposition rate will be very less. Here the deposition rate is very high. So we'll discuss why it happens and what will be the effect of this. any complicated shapes can be manufactured by using this. See how we are achieving the surface finish beautifully. Okay. See, the direct energy deposition from the nozzle, only molten material comes out. Okay. So, and it is being deposited in the substrate material. See, when you look at this video, see, the argon gas or the shielding gas plays a major role. See, the purpose is when the material is heated or the material is heated at the elevated temperature, there is a possible to react with the environment. Then it is possible for the formation of oxides. If the oxide is formed, then it will reduce the mechanical properties of the particular material, because of which the molten material has to be isolated from the environment to avoid the formation of oxides. Okay, to do this, the inert gases are being used to isolate the molten material from the environment. Okay. Here, the inert gases such as argon, helium, hydrogen, or combination of argon and helium, or combination of argon and hydrogen can be used as the inert gas for protecting the molten material from the environment. Okay. See, when you look into argon with 99% of purity is being used for the additive manufacturing applications in the most of industries. Okay. The inert gas should be the flow rate or the correct flow of inert gas should be followed. If it is not followed, then you will not be able to achieve the correct product, since there will be formation of oxides, which will drastically reduce the weight of the mechanical properties of the particular materials. Hence, the inert gas playing a major. So you can use the electron beam also for the direct energy deposition process. See, as I said, the volume of deposition is much more high when you use the wire as the feedstock material. Okay. Here, wire is being used as the feedstock material, and direct energy deposition uses the beam to melt the wire. Okay, so you see the wire is protruded from the nozzle. Okay, see the wire is protruded, and the wire is heated by the laser beam directly, and the molten material is being deposited in the substrate material. Okay, molten material is deposited. Okay, so the protruded wire is being melted by the beam heat source, and the molten material is being deposited on the substrate material layer by layer. Okay, so when you use wire, the deposition rate will be much more high. Okay, so and the when you use what we call powder, so powder, the deposition rate will be much lesser than the wire-based additive manufacturing process. See the surface finish when you use wire. See the surface finish when you use wire, and see the surface finish. See the surface finish when you use. See surface finish when you use powder material. When you use powder material, okay. I told you, so the powder is coming. So when you use powder material, how will be the what we call surface finish? Okay, when you use this one wire, the surface finish is different. Okay, so see the surface finish. So you need to consider a lot of factors and parameters to choose the particular additive manufacturing process to suit your application. This one you can use equivalent heat source or any equivalent heat source to melt the wire, and the melted wire can be deposited on the substrate material layer by layer vertically in order to obtain the final product. So you can use wire arc also heat source. Let's see. Okay, yes. So laser beam, the scanning speed of the heat source and the feed rate of the materials are helping us to achieve the very good product when you go for additive manufacturing, and also the controlled process parameters will help you to achieve the quality final product. And when you use the powder fed fusion process, the powder are spread on the substrate material. Okay. See, in the direct energy deposition, the material, either powder or wire, is melted by the heat source material, melted by heat source, and the molten material is deposited on the surface. When you go for powder bed fusion process, the powder is spread on the substrate material. Okay, there will be no heating. The powder is spread on the substrate material. Then the powder is selectively melted or selectively sintered in order to form the final product, or in order to form the first layer. Okay. See, over the substrate material, the powder is spread. Then the laser heat source or electron beam heat source will selectively melt or sinter the powder in order to form the first layer. Then over the first layer, the powder will be coated or powder will be spread. Then selectively, the layer will be formed as I said for the previous layer. Then powder will be spread. So like this, the final product will be formed. Okay. See, when you form the first layer, after forming the first layer, this will come down. This will come down, and one layer of the powder will be spread. The other will be spread. Okay. Then the up and downward motion of these two are being done when a layer is formed. Okay. So let us see with the video. See, the 3D model is imported. See, when you go for traditional manufacturing system, when you go for manufacturing the traditional manufacturing system, first if you have one machine, first you need to process a product in the machine. Then you have to take the second raw material to process the second product. Then the sequential operation will happen in the traditional manufacturing system. Then if you want to manufacture the more number of products, then you have to carry out the operation parallelly by investing different machines. Okay, when you invest in the same machine, or when you increase the number of the same kind of machines in order to manufacture the particular product, then certainly it will increases the cost of investment. Okay. Whereas in additive manufacturing, you can manufacture the number of products based on the dimensions of the particular machine, or particular capability of the particular machine. You can manufacture more than one product in the bioadditive manufacturing, especially in the powder-based diffusion process. Okay, see, there are 16 components are being manufactured at a time. 16 are manufactured at a time. Okay, if you want to manufacture the traditional manufacturing system, you go to process one by one. If you have a single machine, then if you want to carry out the operation parallelly, then you need to manufacture. You need to have a different machine of same kind. Okay, so this is one of the advantages of additive manufacturing. So after the mods imported, so you see, the first layer has been imported already. Then it selectively melts the particular layer, or the formation of particular layer. Okay. So the inert gas plays a major role, especially in the inert gas will play a major role, especially when you go for nickel superalloys and titanium formate, okay, or zirconium. Okay. So when these materials have the high possibility of reacting with the environment to form oxides. So when you use these materials, especially, you need to have the inert gas to isolate the molten material from the atmosphere. See, one layer of the powder is spread on the substrate material, or previously formed layer. Then the excess powder is being removed. The particular powder layer deposition will be equal to the thickness of the layer, which needs to be maintained. So now it is being selectively tilted. Okay, then you'll be able to remove the component. So you can use blower. Okay. When you carry out this operation, you should wear mask. You should wear mask because all are nano-sized particles. If you inhale or any particles, any metal particles are being accumulated into your body, it will create some problems. Hence, safety precautions have to be taken carefully while doing this operation. So this is the final product which has been deposited or which has been manufactured in the substrate material. This is a substrate material. Now we need to remove the material from the substrate material. Remove the product from the substrate material. So titanium plate or any you can use different products for the fluid flow applications, for electrical application, biomedical applications, and heat exchanger are being made with the help of stainless steel. Tendril implants, teeth are being made with the help of additive manufacturing. Okay. So additive manufacturing helps in different way in forming product like this. So how the molten materials are being formed? So one layer. Okay. So heat transfer modes. Okay, are playing a major role. Heat transfer mode playing a major role in the additive manufacturing. So we know 3 modes of heat transfer: conduction and convection, radiations. So you should have thorough understanding of these 3 modes of heat transfer. Okay, and see how this is the nth layer. This is the nth layer, and this is the n+1 layer. N+1 layer. Okay. So between the nth layer and the n+ layer, see how the conduction heat transfer is playing. Heat transfer is playing. How the molten material is formed. Molten material formed. Even though the molten material is of a tiny size and it is existing for few seconds, see the effect of formation of molten metal will influence the mechanical and metallurgical property of the formed product. Okay, so then this is the direction, scan direction. So the convection between the top layer and the air is because convection is possible in front of the fluid with the presence of the fluid medium. Hence, this air or this environment and this layer will exchange the heat with the help of convection process. Okay, and we know that the bodies which are above 0 Kelvin will emit radiation. Then certainly this will emit radiation. There will be radiation losses. Okay. Then the conduction, convection, radius, and 3 modes of heat transfer are playing a major role in forming the molten pool. And in turn, the molten pool is existing for few seconds and of few centimeters of dimensions, has a lot of effects in the mechanical and metallurgical properties of the materials. And so this is the laser beam diameter, and the laser beam diameter and the hatch distance and layer thickness are also playing a major role in forming the particular products. This one. Eight. Yeah. So you have seen direct energy deposition and powder bed diffusion process. Okay, the direct energy deposition process, the material will be melted first, and then the molten material will be deposited on the substrate material. Whereas in the powder bed diffusion process, the powder will be spread on the substrate material, then heat source will come and it will selectively melt or heat the particular powder material to form the first layer. Then next layer of coating will be done, powder coating will be done. Then it will be selectively melted. Then the particular product will be formed. So these are the difference between the direct energy deposition and the powder bed diffusion process. In the ultrasonic additive manufacturing process, the seeds are arranged together over one by one, one above one. Then, so this is the ultrasonic. So the ultrasonic vibration is produced. Because of the ultrasonic vibration, heat will be generated. Because ultrasonic vibration, heat is being generated. And see, this will vibrate in this direction, and also it will be rolling in this direction. Okay, so this will vibrate in this direction, and it will be rolling in this direction. Okay, so because of the vibration rolling, the heat formation will help you to accumulate the heat in this direction. Okay, in this direction. So this is the accumulating direction. So this type of additive manufacturing process is the ultrasonic additive manufacturing process. When you look into this, here the material is not heated to its melting point, So it's a solid state additive manufacturing process. It's a solid state additive manufacturing process. In the solid state itself, the materials are binded together. So this is ultrasonic additive manufacturing process. And in the binder jet additive manufacturing process, the binder or ink is being used. Liquid binder, liquid ink is used. So one layer of the powder is being spread. Then the binder is used where the particular product needs to be formed. Then another layer is coated. Then the binder will be applied. Okay, binder applied. So like this, the final product is being applied, being manufactured using binder jet process. Then fused deposition modeling or fusion deposition modeling are fused filament debris fabrication, FDM or triple F. Okay, so all are same process. See here the feedstock material is available in the form of material spool. Then it comes out to the it comes out from the nozzle as a molten material. In the nozzle, the material is being melted with the help of electrical energy. That means with the help of a heating element. Okay, so the molten material is coming through the nozzle. So where it is being melted, it's being melted with the help of heating elements. And when it comes through the nozzle, the molten material is coming out. Then the melted material is deposited on the substrate material or on the built platform in order to obtain the particular product. So the motion system is helping us to obtain the final product as per requirement in all the additive manufacturing process. The motion system and their feedstock material and the heat source are the three important systems when you go for additive manufacturing process. When you think of additive manufacturing process, three things should come into your mind. First one is heat source material, then feedstock material, then another one is motion system. Okay. These three are important systems which help us to successfully execute the additive manufacturing process. And sometimes you can go for using the single, instead of single pool, you can go for multi-material, or you can go for multi-spool. Here, see, the 2 spool of materials are being used, and the 2 materials are coming out from the nozzle, and based on the requirement, since they have been synchronized, the particular product can be formed. And when you use the 2 nozzle, when you use the machine with 2 nozzles, the deposition rate will be double. And the time to manufacture the particular product will be very less, because of which the dual nozzle FDA machines are being familiar among the community. And the fusion deposition modeling is very low cost equipment. Even it is available for 10,000, 15,000, 20,000. And most of the education institutions are having these types of machines in order to enhance the knowledge of the students. So direct ink writing is also one of the additive manufacturing process, which is being used in making of sensors, is using of sensor or any electronic components. So so you can use any ink, direct ink, or you can use any polymeric gels or emulsions, and they can be used as the direct ink writing materials. So sheet lamination. So sheet lamination is also being used to manufacture the chemical equipments. Chemical equipments. The sheet lamination process also being used. So 2-photon ionization, aerosol cell printing. Aerosol printing. So what happens? The liquid particle, the liquid feedstock material is allowed to flow through the deposition head, where the because of the vibration, the liquid droplets are being formed, and these liquid droplets are being used to form the layer by layer in order to achieve the final product in the aerogel cell printing. And bioprinting, so you will be able to grow or deposit the cells, nutrients, or other biomaterials layer by layer to produce tissue culture, tissue-like structures, biocompatible scaffolding, upon which additional cells can be grown and developed. Okay. So bioprinting is becoming famous nowadays in the 3D printing. So in order to have the effective bioprinted product, so the data acquisition system is much more essential, and material selection, bioprinting, and functionalizations. So these 4 are highly essential in order to have the 3D bioprinting. And 4D printing. The 4D printing, so when the particular printed material is able to change its shapes and size when it is exposed to external stimuli. Okay, the external stimuli may be the temperature, pressure, or solvent, or maybe when you touch it may happen, or the pH variations, or shear stress, or electromagnetic radiation. Okay, so when you induce the particular product with this, when you external stimuli, then it is possible to change its shape and size. Okay, so that type of products also can be used or can be printed by using the 4D printing. Okay, so polymeric materials are being highly used when you go for chemical applications. Then polypropylenes are also being used to manufacture some items in the chemical industry, in order to apply the 3D printing in the chemical industry. And this being used for the analytical chemistry in the application of chromatography. Okay, so chromatography is one of the most popular techniques which is being used for separation of the mixtures, and records the stationary phase with the precisely ordered morphology to improve performance in the industrial analytical methods. Okay, so chromatography application is one of the famous application in the chemical industries. So the application of analytical chemistry, the 3D printing also nowadays being used. And the 3D printing is being used for printing the electrodes. It's being used for the printing electrodes. So you can use the different layers with the different materials using the additive printing, the 3D printing as per your requirements. So the 3D printing is being used to manufacture the microfluidic devices. Okay, so one is nothing but microfluidics are the micro channels which are being manufactured by using 3D printing, and polydimethylene silzone is one of the most commonly used material to fabricate the microfluidic devices. So 3D printing devices are being used for spectroscopy analysis, and the additive technologies is nowadays highly used in chemical synthesis. When you manufacture the laboratory ware with the material what you require, then the chemical synthesis will be using the particular product, Hence, the laboratory wares are being manufactured by the FDM printing. Okay. Sorry for the interruption. Okay. So organic synthesis are being enhanced. Organic synthesis are being enhanced by manufacturing the particular common using the 3D printing. See, FD printed polypropylene laboratory reactor meant for multi-step organic synthesis. So modular system for fine organic synthesis. Okay, so when you use the direct writing or FDM process for manufacturing the laboratory wares, then the synthesis process can be enhanced and can be designed or can be defined as per our requirement. Now, okay, so nowadays, paramedical industry, pharmaceuticals also using the additive manufacturing to print the tablets or tablet for packaging applications and manufacturing of drugs. So the 3D printing is being used. See, the 3D printing has been used to manufacture the tablets in the pharmaceutical industry. So this is also being used for chemical education in order to enhance the better understanding of the students in the university and schools. The exhibiting the models for the libraries. They can, in order to give you a better education, the 3D printing plays a major role, and you'll be able to print the different sections of the molecules, by using 3D printing. And how will you characterize the AM process? How when you when you want to implement the additive manufacturing process in your particular industry, for particular applications, what are the characterizations you should consider? Okay, so what will be the production time, and what will be the maximum size of the component that can be manufactured, and what will be the ability of the particular equipment to produce the intrinsic parts, and how effectively the component can be manufactured with the perfect and dimension accuracy will help you to implement the additive manufacturing process in your particular industry. Okay. And also I have shown you when you use the wire, when you use the wire as the feedstock material, the deposition rates is much more higher compared to the powder-based additive manufacturing process. But the accuracy of the product will be much more high when you go for powder-based additive manufacturing process and wire-based additive. Sorry for the interruption. So the deposition rate will be much more higher when you go for wire-based additive manufacturing process rather than the powder-based additive manufacturing techniques. And also, you have to consider the surface finish of the particular product, based on which you need to choose the additive manufacturing process to go with either wire or powder. So then what are the factors which contributes for the surface quality of the additive manufacturing products? The alloy type, powder shape, size and morphology, and laser or electron beam focal spot size. Okay. The spot size also will be playing a major role when you go for powder-based additive manufacturing process, and the powder shape and size and morphology also will be helping you to achieve the product with good surface finish or surface quality. And the feedstock material plays a major role, as it was discussed earlier. The surface morphology of the particular powder will be yielding morphology of the particular powder will be yielding these very good surface quality of the product. Then you need to the powders are being manufactured by different manufacturing processes like gas atomization process, rotary atomization process, and plasma rotating electrode processes. So these are the three major processes which manufacture the powders. So you can see the better shapes of the powder. You'll be able to see the very good spherical shape of the powder, which was manufactured through plasma rotating electrode process, and this has been manufactured by a rotary atomization process, and this has been manufactured by gas atomization process. Okay, so you need to carefully choose the powder, and you need to know the type of manufacturing process which has been used to manufacture the powder, and this has to be chosen based on the application of the product and how surface quality of the product you require will helping you to decide better. And also you should have the thorough understanding of the heat and mass transfer phenomena along with the fluid flow. And as I said, you need to have the different modes of heat transfer, conduction, convection, radiation, and even I said, even though it is existing for, even though it is existing, the molten pool is of few centimeter diameter, few mm dimension, and which is existing for a few seconds, that they are playing a major role in defining the quality of the product. Okay, so within, even though it is a few dimension, the flow of the particular molten pool is either laminar or turbulent flow, or how will be the different forces which are acting on the molten pool are very much important to analyze or to obtain the particular products. And the metallurgical properties are highly being affected or are being influenced by the molten pool. Okay, hence you should have the thorough understanding of heat and mass transfer and fluid flow phenomena. So it is being used in the, as I said, it is being used for the used in the chemical industries much more. See, it is being used for manufacturing the catalytic reaction ware, catalytic reaction ware, and advanced, being used in advanced geoinformatics, and in manufacturing the small assemblies, and manufacturing the structured catalyst. And if you look into this, how many products have been manufactured for the chemical applications in the year 2010 and 2021, you'll be able to see. And there's a drastic change in the application of additive manufacturing in the chemical industries. So a lot of so monolithic structures for reactors. Okay, monolithic structures are a single piece of porous material that contains various types of interconnected or separated channels. So these monolithic structures are being manufactured by using the additive manufacturing. See, so we will be able to manufacture the different layers to have the particular structure and particular particular cells. So the different monolithic structures are being manufactured by additive manufacturing. And wire manufacturing, already we have discussed. So the phenomena of conduction, thermal conduction, and how it is being influential in the metallurgical and mechanical properties are already I have discussed. And wire manufacturing, so the process parameter, physical phenomenon, and geometrical features. So when you go for wire cutting manufacturing, then the gas flow, interlayer temperature, the ideal time, are the build set of parameters, and you should have the key input parameters: voltage, travel speed, current, and the consumables. What is the wire diameter? What is the silting gas you are using? And what is the wire feeding system you are using to feed the consumables? And the path planning, how it is being sliced, and what is the path strategy you are using? And what is the post-heat treatment you are using to obtain the final product? And the physical phenomena, what is the reheating cycle, what will be thermal gradients, and how it is being solidified, and what is the melting cycles, and cooling rates, melt pool size, and stress strain and resources, formation of resources are being influential factors in achieving the quality product in the wire cutting manufacturing. And the geometrical features, track size, what is the width and height of the particular layer and particular product, what is the build height, what is the surface finish, and overhang and porosity. The porosity is one of the important factor which needs to be addressed while manufacturing the product through additive manufacturing. If they are not properly deposited, then there can certainly there will be formation of porosity. So earlier days only you see China, UK, and United States have been concentrating on the additive manufacturing process, wire additive process. Now in India, if you look at India, only IITs have been concentrating on additive manufacturing process of wire additive process. Now almost even private institutions are having the research center for wire additive manufacturing. Because of the time constraints, I am skipping. And so resources is very is a worry when you go for additive manufacturing process. Okay, resources, formula resources. Okay, so they can be carefully controlled by using numerical simulation. Okay, so numerical simulation or computational mechanics will help you to control the resources, because you will be able to analyze, you will be able to understand the phenomena behind the formation of resources when you go for the simulation or computational mechanics. That will help you to reduce or mitigate the resources. So you can go for symmetrical building. So you can find a symmetry. Then you can deposit symmetrically. The material can be deposited symmetrically, by which the resources can be minimized. And also when you can go for symmetrical building. Okay, so the substrate material, so one side you can build, then other layer can be built on the other side. So when you build symmetrically, the balance will avoid the resources cannot be avoided, but you will be able to balance, and you will be able to minimize the formation of resources. So you can measure the resources, and you will be able to go for hybrid manufacturing process when you go for manufacturing or when you go for depositing the wire over the forged common. Over the forged common, you have deposited the wire. Okay, so like this, the wire additive manufacturing is being useful for the repairing operations, So heat transfer phenomena and heat source partitions, a particular heat source model for the numerical simulation will give you a better understanding and will avoid the control of resources and molten pool phenomena when you go for numerical simulation. The heat source model plays a major role. When you go for numerical simulation, the standard double separate heat source, 3D volumetric heat source model, and modified three-dimensional heat source model are being available in the literatures. And I have introduced a heat source model called Dhinakaran's model, which is based on the parabolic Gaussian distribution. So this heat source model also is available in the literatures, which can also be used for the numerical simulation to understand the behavior of the molten pool, or in order to avoid the formation of resources. So this is the Nadar model, the equation, and the heat transfer analysis can be carried out by using any commercially available softwares like ANSYS or Abacus. Okay, you can use ANSYS, Abacus, or you can use the OpenFOAM, which is open source software you can use for the for numerical simulation. And the boundary conditions should be given carefully in order to understand the behavior correctly. Okay. So for the thermomechanical modeling, so the heat source selection is very much important, as I said earlier. Then you will be able to understand the formation of heat source, and the temperature distribution can be understood from the numerical simulation, and by which you'll be able to control the different parameters. And when you go for wire additive manufacturing, in order to understand the mechanical behaviors, so you have to choose, after the deposition, you have to choose the specimens as per the ASTM standard. You have to cut like this, okay, in these different angles. You have to cut the specimen Okay. So I hope. So nowadays, machine learning and artificial intelligence is also highly useful in the situ operations of additive manufacturing. So which is being used for controlling the defective products in the additive manufacturing. So when you find any anomaly, during the manufacturing process in the situ operations, so the feedback will be available to the machine, will be unleashed with the algorithm, and immediately that problem can be corrected during the manufacturing process itself. Okay, so these are the anomalies which are being encountered in the powder bed additive manufacturing process. So these anomalies are the images without anomaly can be fed to the can be taught to the algorithm, machine learning algorithm. Then during the operation, if it finds any anomaly, that means in defective defects in the manufacturing process, immediately it will be able to rectify in the situ operations. So this is being useful by using with the help of the what we call machine learning. Okay, and also machine learning welding also using the machine learning process for the weld quality monitoring. Okay, because of the time constraints, I'm skipping the most of the things, and these are the publications which we have published in the area of additive manufacturing. So we have a center called Center for Additive Manufacturing, where we are highly concentrating on the polymer-based, metal-based additive manufacturing. We are using both wire-based feedstock material as well as the powder-based feedstock material, metal for additive manufacturing. So we are doing research, and these are the references which has helped me to better present my lecture. Without this reference, I could not present the lecture in the effective way. And also at this point of time, I would like to thank Dr. T. Debray, who is a professor in Pennsylvania State University, who is an Indian, who has completed his doctoral degree from IIT Bangalore, and he is one of the eminent personality in the additive manufacturing process. I have referred his material, and also the knowledge what I have gained this discussion also helped me to better present this lecture in effective way. So thank you so much for this opportunity. I thank all the authorities for giving me this opportunity to present or to disseminate my knowledge in this wonderful form. Thank you so much. Hello, sir. Thank you, sir. Hello, sir.
Sivakandan, sir.
Yes, sir.
Yes, sir.
Thank you, sir.
Yeah, thank you so much.
Message and all participants for the question session. Participants have any questions, kindly ask and discuss first.
Sivakandan, sir.
Yes, sir.
So your voice is a little bit lower, sir.
So I invite participants if you have any questions, like the resource person.
Thank you, sir. Thank you.
Sir,
hello, Professor. Could you hear me? Professor, could you hear me?
Yeah, I will hear you, but disturbance is there from your end.
Yes.
I have one doubt.
Yeah, please.
I'm I'm Professor
Kindly
Dr.
introduce yourself, sir, and ask the question.
Yeah, I'll introduce. I'm Professor Dr. Shankaran, Director Arrow, NIIT Coimbatore.
Great,
The
sir.
field
Please.
is- The field is Arrow. I have
Yes,
only
sir,
one
please.
doubt. The doubt is how far the latest technology helps in designing the seed nozzle. They have shown me a nozzle I've seen.
Yes, sir.
How fast it's available to make a design seed nozzle.
Yes, sir. See, lot of research works are going on. So I have seen some of the nozzles when I personally visited the DRDO. So research are going on, sir. So it is highly possible in making the novel CD nozzles. So it is possible, sir. Soon, I hope we'll be getting some very good results in making the CD nozzles. But it is possible. Lot of research are going on, and I hope I have seen miniatures of the particular CD nozzles when I visited. But it is possible, sir. It is possible to manufacture almost all the aerospace products through additive manufacturing. The thing is, the cost incurred in the particular manufacturing process is high when you go for because
I understand.
we should spend, yes, sir. We should spend almost
Yes, correct. Very costly. Thank you,
yes, sir.
Professor.
Yes, sir. Thank you, sir. Thank you so much.
Thanks for having shown me practically the latest development. I am old school of thoughts. Right.
Great, sir. Great, sir. Thank you so much, sir. And since I have planned, this is only fundamental lecture. I did not show any my research findings, sir. Else I have shown.
Not
We also
necessary.
printed some. Yeah.
We teachers wish to show some hints only. That's what we can do.
Thank you so
If
much, sir.
anything
Thank you,
required, I will take your help,
please,
Professor,
sir.
for a
Please, sir.
for a
Please, sir. You can
webinar,
approach me,
Professor.
sir. Please, you can approach me.
You can tell your numbers, sir. Let
yeah.
me note down, sir, so that I
Yes, sir.
take your help, sir.
Yes, sir. Sir, I share my screen. I hope.
Yes, sir.
So yeah.
Seriously, you tell me a number, sir. Note down.
Yeah. This is my number, sir. You can. I hope my number is visible. So you can approach me.
Am I right, Professor?
Yes, sir. You're correct.
994-416-17332.
Yes, sir. Yes, sir. You can approach me this number, or you can send a mail. Those mail address. I'm always ready to.
I'll call you.
Participant. Yes, sir. Please. Participants, I am ready to help you. If you want anything in additive manufacturing, if you want to collaborate with me, you can contact in future. Thank you so much.
I'm a good friend of Assistant Professor Balaji.
Oh,
you know him, Professor. Yes, he's with me.
Okay, sir. Good, sir. Good, sir. Good, sir. Thank you, sir. Thank you so much, sir.
Yoganand, sir.
Yes, sir.
Sir, you can ask the queries, sir.
Yeah. So, we will end the session, sir, with vote of thanks. I will call Mr. Nagarajan to propose a vote of thanks. Nagarajan. Sir, project manager, kindly admit Mr. Nagarajan.
Good afternoon, sir. Good afternoon, everyone. First of all, my sincere thanks to Almighty God for making today's event as a grand success by His blessing and grace. Next, I would like to thank our management, Theni Nadar, and our secretary, Mr. K.S. Kasiprabu, sir, and joint secretary, Mr. A. Rajkumar, sir, our beloved principal, Dr. C. Madali Sundaram, sir, vice principal, Dr. N. Madhavan, sir, head of department, Mr. A. Vembatharaja, sir, and coordinator, Dr. Sivakandan, sir. On behalf of Theni Nadar Saraswathi College of Engineering and Technology, I give a really heartfelt vote of thanks to our chief guest, Dr. V. Dhinakaran, Dean, Research and Methodology, Chennai Institute of Technology, Kundrathur. Sir, today we had the opportunity to hear your thoughts, and this is definitely encouraging us in our future events, sir. So thank you for the great occasion, sir. So thank you, Dhinakaran, sir.
Thank you, sir. Thank you so much.
Thank you so much, sir.
Thank you all. Thank you so
Thank you,
much.
thank you,
Yes.
thank you.
Thank you, sir. Thank you, Sugandhan sir. Thank you.
Dr. Sogandan, sir, thank you, sir.
Thank you, sir. Thank you, sir.
Thank you. Thank you.
Okay, sir. Yes, sir. Thank you, sir. Once again, in another occasion. Okay. Yes, sir.
Sir, the feedback link was shared the chat, sir, both the YouTube and Zoom.
Okay. Participant, kindly give your feedbacks. It will be shared in the YouTube and the